Our second unit is going to focus on probability and how to calculate various probabilities in different contexts. So we're going to start out with basic probabilities. And so that question we're going to answer is, how do we calculate basic probabilities? And as always, we need to start off with some vocabulary to make sure we understand what we're talking about. The first vocabulary word we need to know for probabilities is what is called the sample space. The sample space is a list of all possible outcomes. So for example, if I was to flip a coin, the sample space would be all possible outcomes. I could get a heads, or I could get a tails. Which begs the question, what is an outcome? So let's define an outcome really well. An outcome is just the result of an experiment. So an experiment might be flipping a coin. An outcome would be just maybe heads or just tails. And hence the sample space is all of the outcomes, heads and tails. When we're looking at the number of outcomes that occur in a sample space, what we're really interested in finding is some type of probability, or the chance that an event will occur. And what we really end up with is a scale from 0 to 1, where 0 means the event certainly will not happen. Not going to happen. And then the number 1, the maximum probability, is it is certain to happen. And then you could get any decimal in between. So if I ended up with like 0.5, that would be right in the middle. So it's equally likely to happen or not happen. So if the probability is 0.001, it's probably not going to happen, but it could happen. If the probability is 0.95, it probably will happen because it's closer to 1, but it might not happen. The scale from 0 to 1 is our probability. And there's two types of probabilities that we're going to be looking at. The first is called the theoretical probability. Which basically says what we expect to happen or what should happen. And the way we calculate a theoretical probability is we say that the probability of some event E is equal to the number of outcomes that we are looking for divided by the entire sample space, or how many things could occur. That's our basic probability formula. So for example, if I flip a coin and I want heads, we would say the probability I get a heads is the number of outcomes. There's only one outcome on a coin. Out of the sample space, there are 2 possible outcomes on a coin, heads or tails. And then I would convert that to a decimal. In this course, we'll always use decimals for probabilities to get a probability of 0.05 of getting a heads. That's theoretical probability, what we expect to happen. The other type of probability is called empirical probability. And that is the chance of something happening based on our observations of some experiment. What happened in an experiment? So this is the example of maybe I flip a coin 500 times, and I end up getting 257 heads. Because in actual practice, the probabilities aren't perfect. I'm going to get a few more heads or a few more tails. It's not going to be exactly even. And so in this case, the probability of a heads as an empirical probability or an observed probability is 257 out of 500, which is 0.514. There's usually going to be a slight difference between the empirical probability and the theoretical probability. But that difference can be made smaller using what's called the law of large numbers, which basically says that the more trials I do, the more trials done, the closer the empirical probability is to the theoretical probability. If I were to do 1,000 trials, this would be closer to 50%. If I would do 1,000,000 trials, flipping a coin would get closer to 50%. More trials, the closer they're going to be. Now that's really basic probability, but we do have some specific probability formulas to help us calculate some more involved situations. And these 3 formulas we're going to look at are very closely related. They really come as a group. There's no one you should learn before the other because they're all so closely related. So we'll do our best to define them one at a time when really they all come as a group. The first is what we're going to call the conditional probability. In a conditional probability, we write it as the probability of B given A, or with a vertical line between B and A. And what that means is that is the probability of B given A has already occurred. That's a conditional probability where we have some information, and that's going to change the probability of B. The formula for a conditional probability is the probability of B given A is equal to the probability that both occur, A and B, divided by the probability of the given information. In this case, the probability of A. That conditional probability formula will be very important to us. We'll do an example here in a minute. But let's go on to the second type of probability we need to know. And that is the AND probability. The probability of A and B is the probability that both occur at the same time or together. And the formula for the probability of A and B comes from the conditional probability. If we multiply both sides of the conditional probability formula by the denominator, the probability of A, we end up with the probability of A times the probability of B, given A has already occurred. And that is the conditional, I'm sorry, that is the AND probability formula. The third formula we need to know is the OR formula, the probability of A or B occurring. And that is the probability of A occurring, or B occurring, or both occurring. One or the other or both. And the formula for an OR, the probability of A or B, is we're going to add the probabilities together. The probability of A plus the probability of B. The problem is this counts the AND or the overlap twice. It counts it in the probability of A, and it counts it in the probability of B. So we have to subtract off the overlap, or subtract off the probability of A and B. So it's not double counted. It's only counted once. And that gives us our formula for the OR. Those are our three probability formulas. The conditional probability is the probability of both divided by the given information. The AND probability, with AND, we multiply the probabilities together, given the first one's already occurred. And with an OR probabilities, we add them together, subtracting off the overlap. So let's do an example, number 4. Let's say we have 3 blue cards numbered 1, 2, and 3. And we also have, let's write 3 out as a number since it's starting a sentence. 3 blue cards numbered 1, 2, and 3. And I have 2 yellow cards numbered 1, 2. A, we're going to find the probability actually, let's just write as a probability statement. We're going to find the probability that I get a blue card given the card is even. With a conditional probability, since I know the card is even, we're not dealing with all 5 cards anymore. We're just dealing with the even cards. So we find the probability of both blue and even. From the blue cards, there is one that is blue and even. So there's one of them out of the 5 cards, divided by the probability of the given information. The given information is that it's even. There are 2 even numbers out of 5. Now, what's nice is generally those denominators will divide out, and we're just left with 1/2, or 0.5. So that means if I know I've got an even card, the probability is 50% that it's going to be even. That's conditional probabilities. Let's find the probability that I get a blue card and an even card. Now, this is looking for the probability that both occurred at the same time, blue and even. Of the blue cards, only one of them is blue and even. Out of the total cards, now we're looking at the total sample space, of 5. And so the probability that it's blue and even is 0.2. There's only a 20% probability that it's both blue and even. What about the probability that it's blue or even? For blue or even, now we're looking for how many are blue. The first option, there are 3 blue cards out of 5, plus how many are even. There are 2 even cards out of 5. But then we need to subtract off the overlap, the ones that are blue and even. Blue and even, we know there's only 1 out of 5 that's both blue and even. So 3 plus 2 minus 1 is 4/5, which means we have a probability of 0.8 that it is blue or even. I want to do one more example that kind of illustrates the AND formula maybe a little bit better. And that is finding the probability that if I draw 2 cards with replacement, actually, maybe I should write this out. Probability I draw 2 blue cards without replacement. What I'm really saying is, what's the probability the first one is blue? And what's the probability the second one is blue? Well, for the first one to be blue, the probability of the first event, there are 3 out of 5 that are blue. Then we multiply by the second event, the probability that I get a blue, given the first one was already blue. So now one of the blues is gone. Maybe the 2 is gone. Now there's only 2 blues left. Out of, there's only 4 cards left. And when I multiply that across, we end up with 0.3 is the probability we get 2 blues without replacement, 30%. So that's what we're looking for with that AND formula. The second part, the AND, we adjust the probability to assume the first one already occurred. Those are our basic probability formulas, but there are 2 vocabulary concepts that are related to those that I want to make sure we are familiar with. So the first one of those 2 is what are called independent events. When 2 events are independent, what that means is one occurring does not change the probability of the other occurring. The opposite of this would be dependent events. And if we think about the blue cards that we drew without replacement, the second probability was 2/4. That second probability had changed from the first probability because one occurring changes the other one's chance of occurring, because there's fewer cards left. There's fewer blues. Now, the way we show things are independent, we can show this in one of 3 ways. And it doesn't matter which one of these ways we use, so we'll just pick the one that's most convenient for our context. The first is we can show that the probability of A, given that B has occurred, if B is not going to affect its probability, it should still be the same as just A occurring by itself, because B has no impact on it. The opposite is also true. We could say the probability of B given A is going to be just equal to the probability of B, because A occurring has no impact on it. Or the third method we can look at is the probability of A and B. The probability of both of them occurring is equal to just the product of the individual probabilities, because the given part doesn't change. So for example, let's say in a class, 20% of students are left-handed. Five percent of students are earning an A in the class. Good job to those 5%. But only 1% of students are left-handed and earning an A. Are these events independent? Is there a relationship between left-handedness and earning an A? Well, we'd have to look. What's the probability that they're left-handed? We're told the probability they're left-handed is 0.20, or 20%. The probability that they're earning an A, of all students, 5% are earning an A. So the probability of earning an A is 0.05. We're also told the probability of the students who are left-handed and earning an A, both of them together, is 0.01. Well, we can use either one of the three formulas for showing things are independent. It's probably going to be easiest in this context to use the third, because we have all of those pieces. So the probability of A and B, the probability of left and receiving an A, should be equal to the probability of being left-handed times the probability of receiving an A, if they are in fact independent. Well, the probability of A and L is 0.01. The probability of left-handed is 0.2. The probability of an A is 0.05. And sure enough, we get those are equal to each other. Because they're equal, we'll say, therefore, they are independent events. If it wasn't equal, we would say the opposite, or that they're dependent events. So that's the first concept, the idea of independent versus dependent. The second concept that I want to wrap up with today is the idea of mutually exclusive. Two events are mutually exclusive. That means both cannot occur at the same time. Essentially, what we're saying is the probability of A and B is equal to 0. An example of this would be if I were to roll a die, a standard 6-sided die, and we're going to let O, actually I'm going to use the letter D because O is a bad letter for math. D is going to represent an odd less than 4. B is going to represent a number bigger than 3. So what you see is D, the odds less than 4 are the numbers 1 and 3. That's kind of the sample space of D. And B, the event B, is everything bigger than 3, which is 4, 5, and 6. These two have nothing in common. You can't both be an odd less than 4 and a number bigger than 3. Because we can't have both together, we say they are mutually exclusive. In other words, the probability that we have an odd less than 4 and a number bigger than 3 is equal to 0. That never happens. So a little vocabulary as we wrap up with mutually exclusive. Both can't occur at the same time. Independent, one occurring does not affect the other occurring. But the big thing that we're looking at today are these probability formulas, conditionals, ands, and ors. Take a look at the homework assignment to practice a few of these. We will try a few more in class and answer any questions you might have then.